Now I'm going to talk about least squares prediction. As you consider that I have an unknown parameter at point P, and I want to estimate it from the measured value around it. Let me call this measured value L. Then I define an estimator, which is in fact a linear combination of all these parameters, all these things between point P and each point and each measurement. This is the estimator or the linear estimator. This estimator should be best among all classes of the estimator plus unbiased. Then we will see how can we do this. Let us assume that, okay, this measurement L has the error, the random error, I would say, epsilon I. And if I subtract the true value of xp from it, then in this case, I will get mean square of something like that. This, if I rewrite it, you will see that that's the error equation. And this error equation should be minimized. How we cannot minimize it directly, but we try with the square of this equation. So it is that m2x tilde p should be minimized. The first term is the random part contribution of the random error, and this one is actually the bias. In fact, we will minimize both of them, or the summation of the random part and how. We should first square this equation. Thereafter, I will explain what they are actually, how they are connected. So far, I can say that if this is random error, then this expectation should be 0. Then I do not bother myself with that. So I will write it in red here. The expectation of M2 P is, what is this? Let me use another color. This is actually the covariance matrix or error covariance matrix. So this one is the autocovariance matrix between L and L. And this one is the cross covariance matrix between X and L. So that means that these are the definitions that we can use for the covariances, for covariances between them. So therefore, instead of these things, I will directly write the equation based on the covariances directly. Based on the covariances directly. In this case, I will get okay, let us continue. Let me write this equation again in another form. So derivative of this, let me. This should be equal to 0. If I solve this API, it means that I come to a system of equations. This is a system of equations having page A page, this A page A, which I see as unknown, and these are as a noun, and these are the covariant functions. Then if I write this in the matrix form, so if I, for example, if I come back to the estimator at point, that it is not, it's not possible. Should be written like that. So that's the principle for least square prediction. So for it's also least square collocation is also working with the same principle. But these covariance functions comes from other sources, for example, from a mathematical model. So we have a cross covariance, and then we have autocovariance, this cross covariance, and this is auto covariance, and this is error covariance function, or the variance covariance matrix. So this means that if I have a space of the prediction and a space of the observation, and this space has its own covariance matrix, and this has autocovariance matrix. This covariance matrix explains the relation between all parameters in this space, X space, and the other one for the other. And we have a transformation between these two transformations. So, for example, with this equation, Rx equals to L. Then if I apply A instead of say XX, I come to XL, LX, XL, LX, this will be LX. And if I have CXL will be CXX A transpose that I have. And if I apply error propagation, something like covariance propagation, so what we can see here, if I perform the prediction in the same space, for example, only in X, what I get from X cap. So X cap was this equation. Let me write it in another one. So if I work in a space, then I will have say XX plus C epsilon epsilon, if you remember, multiplied by X. Let me clean this part to explain better. What, and it was multiplied by X. So what does this say? It's a vector of X. When you multiply, so X is, if we do not have the error here, then it would be 1. It means that what is observed is what it is. What is observed is what is predicted. But since we have the error here, this error doesn't let this to be 1. It will be somehow filter X. This is exactly similar to the principle that we have for Wiener filter. Wiener filter says, oh, if I have the error variance, if I have the signal and I have error of the signal, so if I as long as this one, the signal is stronger than the error. So these two terms Cn will be close to 1. So whatever you get, it's not too much filter. But when this error gets larger, it will start filtering the vector Vx. For example, if Cn is 1 on plus, so it is the error level, and this is 1. As you see, it doesn't matter. At the end, it's approximately 1. But if it is like that, it will start to damp high frequencies faster. So it means that if I have a signal and I have a signal like this, and that for the first case, it will start filtering high frequencies. But in that case, it starts from filtering lower frequencies. Because the error, it means that it is doing some form of regularization. This will smooth the solution, but the smoothness is dependent on the error or the variance of the measurements. That's the principle of least square prediction and least square collocation. But the least square collocation, the only difference that you see, as I have explained, is related to the covariance matrix. So if I have the vector, I have vector of predictions, and I have the covariance matrix between the measurements and the unknown. Then I have the autocovariance function of the measurements plus the variance covariance matrix of the measurement, multiplied by L vector. In that case, it will start these errors will start smoothing the solution, filtering the solution is here, and this cross covariance is actually will change the space of X to a space of measurements, or L to a space of the prediction. That's the whole principle of least square collocation, which is this one.